The natural logarithm. So you probably learned about logarithms in your algebra class, but the natural logarithm is a special subset of logarithms with base e. So we talked a little bit about the number e in the exponential functions video, but e is just a number. It's approximately 2.71 that tends to come up in nature. So when you take a logarithm with base e, it's called the natural logarithm, and it's written with the acronym ln. So the natural logarithm of x, we're going to write as ln of x, is the power of e needed to get x. So when we do this, we're looking to figure out what that power is. So if we know that the natural log of x equals c, we're saying, what does c have to be in terms of a power in order for e to the c to be equal to x? The primary use of the natural log for this course is going to be to help us solve things algebraically. We won't be using other logarithms. However, we will need to know certain properties of the natural log in order to help us solve these things that are typically related to growth and decay. So one of the most important things that we're going to need to remember is the domain of the natural log of x. So the natural log of x is only defined when x is strictly greater than 0. So that means the natural log of x is not defined for negative numbers or 0. So keep that in mind when you're solving problems. If you end up having to take the natural log of a negative number, something has gone wrong. So there are three properties of the natural log that we're going to want to remember that we're going to be using throughout this course. The first is that the natural log of 1 equals 0. The next is that the natural log of e equals 1. And then finally, if you take the natural log of a number raised to a power, so think exponential functions here, that power can come down in front. If you're wondering what natural log looks like, it's going to have this shape here. It's going to come up. It's never going to be negative for x, so it's going to approach. We're going to have an asymptote at 0. And here, this is going to happen at x equals 1. So the natural log of 1 is 0, and these are all positive x values where this is defined. So as I mentioned before, we're mostly going to be using this to solve growth and decay problems. There are a few other algebraic properties of natural logs that might come in handy, so let's quickly review those and then we'll try some problems. So first, if you have the natural log of a times b, so if you're taking the natural log of two things multiplied together, you can separate those by addition. So you can take the natural log of the first thing plus the natural log of the second thing. If you have the natural log of a ratio, a over b, we can split that up as the natural log of a minus the natural log of b. If you have the natural log of something raised to a power, so the natural log of a raised to the power p, the power comes down out front. That's the same property we had up here, and this is the one that we are mainly going to be using throughout this course. And then a subset of that is if you have the natural log of e to the x, that just equals x. So if we were to apply rule 3 to the natural log of e to the x, we would get x times the natural log of e. But remember, the natural log of e is 1, so that's why we just get an x back. Similarly, if you have e to the ln x, that's just going to be x. So keep in mind some of these properties as we work through these. Again, the main purpose that we're going to have for the natural log is to help us with some algebra stuff. So let's take a look at an example and see how we use the natural log to help us solve for a variable. Example 1. For each of the following equations, solve for t. So again, the main purpose here is when we're dealing in exponentials, trying to solve for that power where our independent variable is going to sit. That's why we're going to need to invoke the natural log to help us along the way. So for a, we see that we have the power t up in the power, and we want to solve for that. So if we take the natural log of both sides, the natural log of 4 to the t equals the natural log of 10. right? So just like anything else, if you do it to one side, you have to do it to the other side. So when you use the natural log, you're going to do it to both sides. And that's going to lead us to a new equation using our property that the t can come down out front. We have t times the natural log of 4 equals the natural log of 10. So that t power came down out front from the rule we had earlier. So if we're solving for t, we get t equals the natural log of 10 divided by the natural log of 4. I just divided this term over to the other side. Now, here's an important distinction. If I'm solving for t and I'm looking for an exact answer, if I see the word exact on my homework or on an exam, this is an exact answer. We leave the natural logs in there. If, however, it says find t to 3 decimal places, something of that sort, then we would plug in the natural log of 10 and the natural log of 4 into our calculator because that's going to give us an approximation. So the wording of the problem is incredibly important. As soon as we plug this into our calculator, it becomes an approximation because when we use the natural log, it's going to round out some numbers for us. So if we were to plug this in order to get a decimal, we would get approximately 1.66. So I'll write that underneath this. So t is approximately 1.66. So again, this top one is an exact answer because we didn't do any rounding, and this is an approximation. Okay, so let's look at number 2. Number 2 is slightly different because now we have something multiplying the 3 to the t term. So it is another exponential function. But before I apply natural logs, I really want to try to isolate the term with the variable in it. And it's pretty straightforward to divide here. So my first step is going to be to divide both sides by 2. So if I do that, I get 3 to the t equals 4. Then I can take the natural log of both sides. So the natural log of 3 to the t equals the natural log of 4. Again, my t can come down out front, and then I can divide. So my t will be the natural log of 4 divided by the natural log of 3. So again, that's an exact answer for number 2. And if I'm asked for an exact answer, that's exactly how I want to report it. Be careful and make sure you use parentheses when you have the argument. So the natural log of parenthesis for close parenthesis, just for syntax reasons. If I wanted to turn this into a decimal, I could plug it into my calculator and I would get that this is approximately 1.26. But again, as soon as I throw the natural log into a calculator, it becomes an approximation. So for part C here, again, I want to try to isolate the term that has the variable before I apply any algebra rules to it. So I'm going to start by adding the 7 over to the other side. So I have 5 times 2 to the t equals 15. Then I'm going to divide both sides by 5 to try to get rid of that 5. So I have 2 to the t equals 3 because I divided 15 by 5. I'm going to take the natural log of both sides. So the natural log of 2 to the t equals the natural log of 3. The t will come out front. So my t is the natural log of 3 divided by the natural log of 2. Again, this is an exact answer. And if I want to turn this into a decimal, I can plug this into my calculator. And again, if I do that, it will be an approximation and no longer an exact answer, but I can certainly do that. And I will get 1.58. Okay, so the key thing here is that I'm always trying to isolate the term that has the variable before I take natural logs. That makes all the algebra easier. Let's look at another one. So for example 2, we want to consider the function w equals ae to the bt using natural logs to solve for t. So this is similar to what we were doing before, except now we don't actually have any numbers, except for e, which is approximately 2.71. But we want to be able to solve for this algebraically, even if we have variables instead of numbers. So we're going to take the same approach that we were using before, and we're going to start by trying to isolate the term that has the variable we're looking for, which is t here. So I'm going to start by dividing both sides by a. So I have w over a equals e to the bt. So now I have that term isolated. I'm going to take the natural log of both sides. So the natural log of w over a equals the natural log of e to the bt. Now, natural log of e to the bt, the power can come down in front. So that's going to be my next step. The left is going to stay the same. So the bt is going to come over here, and then I have the natural log of e. Well, remember that the natural log of e is just 1, and anything times 1 is just itself. So to solve for t, my last step is to divide both sides by b. So I have the natural log of w over a all divided by b. So I was able to come up with the solution for this even though I didn't have any numbers in my original problem. So I just have to follow the same steps of isolating the term with the variable in it and then using the algebra rules I know to simplify as much as possible. Let's look at one more example. Example 3. Use natural logarithms to convert the function p equals 500 times 1.06 to the t to the form p equals p naught e to the kt. So first we need to figure out what we're trying to do here. So we have this function in this form, but we want it to be in this new form. So let's write the new form directly underneath it so we can sort of figure out what we're looking at here. So what we're looking at on the top, we have something that has a growth rate that is constant. So we are growing at a rate of 6% for every time unit. That's the 0.6 part of the base. And what I want to do is I want to change this to what's called a continuous growth rate. So depending on the science courses you've taken, you may have encountered this. But when you have e to the k, we're talking about something that's growing continuously. So what we're trying to do is convert something that maybe we thought had a certain type of growth rate to a different type of growth rate. So how do we convert these things? So here, the 500, that's our initial population in both cases. So that's not going to change. So in my conversion, the 500 stays. The t also stays. That's the same as what's going on here, right? So I can write the parts I know, the 500 and the t, and sort of pull out the e to the k. So if you have a power raised to a power, you would multiply those things together. So we can write e to the k all to the t, and that's the same thing as e to the kt. So when I match these up, that means that I need e to the k to equal 1.06 to convert from the first form to the second form. So that means I have e to the k equals 1.06. Well, e is a number, so that's not something I can solve for. But k, I don't know, right? I figured out p naught, t is a variable, capital P is a variable, but k is the number that I need to complete this. So to solve for k, I can take the natural log of both sides. So I have the natural log of e to the k equals the natural log of 1.06. Again, the k will come down out front. So I have k times the natural log of e equals the natural log of 1.06. So as a reminder from before, if you take the natural log of e, that's going to be equal to 1. So that means I just have k times 1, which is k. And again, if I want this to be exact, I could leave my rate as the natural log of 1.06, and sometimes we do that. But most of the time we're going to round this out and have a decimal. So if I convert this to a decimal, if I do the natural log of 1.06, I get 0.058. So I'm going to write this as 0.058. I rounded this to 3 decimal places. It actually goes on for my whole calculator, as it probably would for you as well. If you are going to be plugging this into your calculator, the problem will specify how many places to round to. So now that we have our k, our final step is putting it all together. So we have p equals 500 times e to the 0.058 t. So now we have a model in terms of e that is equivalent to what we had for our exponential function up here. all because we were able to use natural logs to convert between the two.